Hi, welcome to section 4, the section you've all been waiting for when we finally get to learn about imaginary and complex numbers. This section is very related to previous skills of simplifying square roots from Algebra 1 and geometry. So actually we're going to split this section into two videos, and in the first video we're going to review very quickly how to simplify regular square roots with real numbers. And we're going to start talking about imaginary numbers, and then in the second video we'll finish talking about imaginary numbers, and we'll extend that to complex numbers in general, and we'll see how what we know about simplifying square roots from before relates to simplifying and doing operations with complex numbers. So we have some vocabulary you're going to want to keep an eye out for in this section: imaginary unit, pure imaginary number, complex number, and then something called complex conjugates. So those are the four terms that you want to make sure that you can explain or understand at the end of this video. But remember, we're going to start by just doing some review of radicals in general. So if you remember, when we multiply radicals, in this section we're focusing specifically on square roots, we have the product property of radicals. So if I have something under a square root, I can split it up into two different square roots multiplied together. Or I can also go the other way. If I'm multiplying two square roots together, as long as they both have the same index, which for our purposes in this section is just going to be 2. Remember that square roots always have a 2 there. We just don't usually write it. That's called the index. So as long as the index is the same, I'm allowed to multiply square roots together. I just multiply the radicand, the number that is under the square root. So radicals are simplified when the radicand, meaning the number under the square root, has no factors other than 1 that are nth powers, or in this section we're going to be talking specifically about perfect squares of an integer polynomial. So we want to make sure there are no perfect square factors under the radical sign. I don't want any fractions in the radicand and no radicals in the denominator. And remember, when we have radicals in the denominator, the way we get rid of them is by rationalizing. We're turning an irrational number, like the square root of 5, into a rational number. So we multiply by something so that what's under the square root becomes an exact root, or a perfect square that I can take the square root of. So of course, to do this, we need to remember what our perfect squares are. You should have this list of perfect squares memorized. Maybe if it will come up here. This is on your note guide. And these are perfect squares. So remember that 1 is 1 squared. 4 is 2 squared. 9 is 3 squared. 16 is 4 squared, and so on. For some reason, this list skipped 19 squared, so I wrote it in there. So you should know all the way through 20 squared. You should know all of those perfect squares. And then 25 squared equals 625. That's one that you'll see come up sometimes in problems, so that's a good one to recognize. Remember, what this means is that if I want to take the square root, for example, the square root of 16 is 4, because 4 squared is 16. The square root of 49 is 7, because 7 squared is 49. The square root of 256 is 16, because 16 squared is 256. You need to know this list. So we're going to remind ourselves what it means to simplify a square root. When I simplify a square root, I'm looking for a perfect square factor, right? So I'm looking for one of these perfect squares to be able to be a factor of whatever is underneath the radical sign. So in the case of the square root of 8, 8 is 4 times 2. 4 is the perfect square factor, and 2 is just the other factor. And then what happens is I can rewrite this as the square root of 4 times the square root of 2. The square root of 4 is 2, right? So that just becomes the number 2. And then the square root of 2 stays as is because 2 is not a perfect square. So the square root of 4 is the number 2. And then I leave the other factor underneath the square root. When it comes to 20, again, 20 is 4 times 5. 20 is also 2 times 10, but 2 is not a perfect square and 10 is not a perfect square. So I'm looking for the combo of factors where one of my factors is a perfect square, where one of my factors comes from this list of numbers. So 20 is the square root of 4 times the square root of 5. The square root of 4 is 2, and then the 5 stays underneath. I would suggest that you pause the video and see if you can figure out the next 3. Alright, this is how we simplified the other 3. The square root of 32. 32 is 16 times 2. The square root of 16 is 4, and the 2 stays underneath the square root. 75 is 25 times 3. The square root of 25 is 5. 3 stays under the square root. And then 40 is 4 times 10. The square root of 4 is 2. And the 10 is not a perfect square, so it stays under the square root. Alright, when I'm adding and subtracting square root expressions, the indices, meaning the kind of root that it is, square root, cube root, whatever, and the radicands, the number underneath the radical sign, have to be alike. So basically we treat these like we do like terms. So for example, if I had 2 square root of 2 and negative 10 square root of 2, these would be like radicals because they're both square roots and they both have a 2 underneath the square root. If I had x squared square root of y and 2x squared square root of y, those would both be like radicals because they're both square roots of y. A not like radical would be like the square root of 10 and the cube root of 10. They both have the same radicand, the same number under the radical sign, but one is a square root and one is a cube root. If I have the square root of 12 and the square root of 15, those are both square roots, but one is a 12 and one is a 15, so I would not be able to add or subtract them. So when we look at these examples here, it looks like I can't do any adding and subtracting. But before I add and subtract, I always have to simplify. Oops, I got an extra I in there. Simplify first, before I decide if I can add and subtract. So walk with me through these problems. We're going to simplify. So I have 2 times the square root of 12. Well, I need to rewrite 12 as a perfect square times another number. So 12 is 4 times 3. Then here I have 3 square root of 27. 27 is 9 times 3. 9 is a perfect square. And then here I have the square root of 48. 48 is 16 times 3. 16 is a perfect square. So here my 2 that was already outside of the radical stays outside. The square root of 4 is 2, so I bring that outside, and then the 3 stays underneath. Here my 3 stays outside. The square root of 9 is 3, so I bring that out, and then this other 3 stays underneath. Here I have a 2 out in front. The square root of 16 is 4, and the 3 stays underneath. So this is 4 times the square root of 3 minus 9 times the square root of 3 plus 8 times the square root of 3. And now I look and see, okay, are these like radicals or not? They're all square roots, and they all have the same number under the radical. So I can add these just like I would add 4x minus 9x plus 8x. I just add the coefficients. 4 minus 9 is negative 5. Negative 5 plus 8 is positive 3. So my coefficient is 3. And so I have 3 times the square root of 3. The radical stays the same. Just like if I were to do 4x minus 9x plus 8x, I would end up with 3x. It's the exact same process. Okay, I would suggest that you pause the video and try this next one, even though it's not an ed puzzle question. Okay, and here's the work for this one. 45 is 9 times 5, so that simplifies to 9 square root of 5. 80 is 16 times 5. The square root of 16 is 4. 4 times 5 is 20, so that's minus 20 square root of 5. And then 32 is 16 times 2. So notice here I only have 2 like radicals. 9 square root of 5 minus 20 square root of 5. That gives me negative 11 times the square root of 5. And then the 16 square root of 2 is not a like term. It's not a like radical. So it just stays plus 16 times the square root of 2. And that would be my final answer. Alright, so let's look at some general simplifying here to remember what we do when we have some division, multiplying, and different things like that. So what do we do when we have variables? Well, we know here that 16 is already a perfect square. When I'm dealing with variables, remember that a square root means I have the same thing times itself. So the square root of 16 is 4 because 16 is 4 times 4, right? Well, p to the 8th is p to the 4th times p to the 4th. So it works a little differently with the exponents. And then q to the 7th is q, well, we'll talk about the q in just a second. Let's talk about the p to the 4th first. So the square root of p to the 8th is going to be p to the 4th because p to the 8th is p to the 4th times p to the 4th. Because remember, with exponents, when I multiply things with like bases, I add the exponents. But when I talk about q to the 7th, I don't have an even exponent. I have q to the 6th times q to the 1st, right? So the way that we would simplify this, well, the square root of q to the 6th is q cubed. Why? Because q to the 6th is q cubed times q cubed. But then this q to the 1st stays underneath the square root because it's not a perfect square. Basically, to have a perfect square, I have to have a set of two factors that are the same. So if I were to write out q to the 7th, if we want to have another way to think of this, the square root of q to the 7th, well, q to the 7th is q times q times q times q times q 7 times, right? And so how many pairs do I have? Each pair represents a perfect square. 1, 2, 3. So that means q cubed, 3 of those q's can come out and multiply together. But then one q that doesn't have a pair has to stay underneath. So when I'm doing the square root here and simplifying it, the square root of 16 is 4. The square root of p to the 8th is p to the 4th. And then for q to the 7th, I bring out a q cubed. But one q stays underneath the square root. Okay, in the second example, we have the square root of x to the 4th over y to the 5th. Remember, we're not allowed to have fractions under a radical sign, but I can rewrite it like this as this quotient of two square roots. So I have the square root of x to the 4th over the square root of y to the 5th. So we're going to simplify first. The square root of x to the 4th is x squared. The square root of y to the 5th, remember y to the 5th is y to the 4th times y. The square root of y to the 4th is y squared, and that leaves one y without a perfect square partner under the square root. But this is not fully simplified because I'm not allowed to leave radicals in the denominator. So I need to give this y, another pair, or its partner, so that it can become a perfect square. But since this is not an equation, it's a fraction, I need to multiply by 1, right, so that I don't change the value. So I'm going to multiply the numerator and the denominator by the square root of y. So in the numerator, I'm just going to get x squared times the square root of y. And in the denominator, I get y squared times the square root of y squared, right? But the square root of y squared is y. So my numerator stays x squared times the square root of y. And in the denominator, the square root of y squared is y. Y times y squared is y cubed. So I end up with x squared square root of y over y cubed. All right, let's look at this next example. You can either simplify first or multiply first. Here the numbers are pretty small. They're both square roots, so we can just multiply together. 6 times 2 is 12. A times a cubed is a to the 4th. B squared times b squared is b to the 4th. And then we're going to simplify. 12 is 4 times 3. Why do I choose 4 times 3? Because 4 is a perfect square. A to the 4th and b to the 4th are also perfect squares. The square root of 4 is 2. The square root of a to the 4th is a squared. The square root of b to the 4th is b squared. And then the 3 stays underneath, so this would be the simplified form. Last but not least, here we're going to FOIL. So you can see the work here. 5 square root of 3 times 5 square root of 3 is 25 times the square root of 9. Square root of 9 is 3, so that's just 25 times 3, which is 75. My two middle terms become 30 square root of 3 minus 30 square root of 3. So those add out to 0. And then negative 6 times 6 is negative 36. And the rest of this is just simplifying. 75 minus 36 is 39. Okay, conjugates, if you'll remember, here my denominator has two terms, 5 plus the square root of 3. So in order to rationalize this, I have to multiply by its conjugate. The conjugate is just the denominator with the opposite sign, so we multiply by 5 minus square root of 3. So take a second to look at the work here. The reason that we multiply by the conjugate is that here in the denominator, my middle two terms will cancel, and the rest of this work is just simplifying until I get down to 4